so let's continue. Yeah, so there's the Hungarian dance version. On going back to our quick sort, right? More sorting algorithms, right? So where's my notebook? Oh, here we go. No, I'm signed in. Now I have to find my notebook. Good question. Now where is it? Here it is. Oh yeah, sorry, continue. Yeah. So the point of pivot. So what's the idea? So I hope you see that if you choose a pivot, just taking the first one each time, you might end up with a bad case, right? Of quicksort, the worst case scenario. So what's that? So what are ideas? How could we improve this?
Choose the pivot in the middle.
Yeah, but we don't know what the middle is. That's the only problem. Yeah. So yeah, we can take the middle. We can take the middle, right? And maybe you get lucky, and it's not it's not the smallest or biggest one, right? Yeah. So maybe less chance, right? But of course, if somebody is evil and knows you always take the middle one, they could put the middle. They could come up with also a way of evil sequence of numbers, right? So how could you beat this evil adversary, right? This, I don't know what you call it, Satan, right? Satan's adversary, right? So how could you beat him or them? Well, to me?
You take 3 values and you pick the middle one.
Yeah, that's actually the best approach. You picked on the best approach, best practical approach, right? You take 3, like maybe, roughly. But theoretically, if you had a good way of picking randomly, that would also work, right? If you take random pivot, just take, eyes closed, you take pivot, that will break any, no adversary will be able to beat you, probabilistically, right? And on average, you'll still get this log n performance, because that's actually what you're doing when you're taking the first one. You are counting on the fact that it's random pick. But the issue with picking randomly is, what's the issue? Is that this eyes closed picking is actually hard to do, right? If you, for each pivot, you have to calculate the random values. Calculating random values actually is expensive, right? You need to do this pseudo-random values, right? You need this twister, this Mersenne twister. There's various technologies, but basically, there's not a really good way. So, approach you mentioned. What was your name? Christers. The Christers approach is extremely practical. You take maybe first, last, and middle, and you take the middle one of those. And of course, again, a really evil adversary could figure out how to pick, the numbers exactly. They always all, let's say the first one would be 1, middle one would be 2, and the last one would be 3, right? And you still have a pretty bad pivot, but in practice, you could vary this middle maybe a little bit, maybe, right? So in practice, this works really well. So take 3 values as potential pivots: first, last, middle. Take the middle. It's relatively fast. Obviously not as fast as taking the first one, right? And you have decent pivot. You want basically decent pivot, right? So you don't need a perfect pivot. Perfect would be just right in the middle, right? Then you have nice performance, log n performance, right? So again, a quick sort is very good on large amounts of basically semi-random data. It will be very fast, right? Again, so team sort is basically, turns out you can use this insertion sort for small values and use merge sort for actually merging these smaller sections. Okay, so now we get to this question of pivot. We discussed this pivot selection. Now let's see, can we do anything better, right? So we have team sort, we have, which is a hybrid. We have a quick sort, we have merge sort, and heap sort. Those are all good algorithms, but they're all log n in average case. Like if you check here, right? So n log n. So these are good, right? Now we have some bad ones, right? There's also something called tree sort. I forgot what the tree sort looks like, but we need to check it again. But turns out, can we do better? Right? That's how you should be asking this question. Can we do better? We're doing good. Can we do better? Right. Turns out, it's been proven actually, if you go to a Stack Exchange, right, computer science, it's been proven that you basically, as long as your sorting involves comparisons, you can't beat n log n, basically, right? You still have this n times, right, and log n. So again, what could be potentially like, what is the complete absolute best case scenario for sorting, right? You have already sorted items, right? we discussed this on Tuesday, what's the best case scenario? We have to go through at least one time, right? We have to check it's sorted. I mean, you can't beat that, right? We have no way of saying, okay, we can't randomly sample some values, right, and say, okay, it's sorted. I mean, you can make some probabilistic assumptions. Yeah, you pick 5 values at random, and you can say, okay, there's 80% chance this is sorted. But then, that's usually not used, right? But yeah, so n log n, in general, you cannot beat it. But when can we beat it? So the answer is, you don't compare. And then you might be asking, well, how is it possible to actually sort something without comparing, right? So the answer is, well, there's this range of algorithms. Well, they involve buckets, basically, right? There's counting sort, radix sort, bucket sort, right? Basically, we're going to go through linearly, and we're going to put them somewhere. And I'll show you the basic idea here with dice, right? Let's do some dice. Let's roll some dice, right? So I'm going to use, I have some dice. Not a regular 6-sided dice, not 20-sided dice, right? 6-sided dice, so you have value from 1 to 6, right? And I want to sort them, right? And I have 100 of these dice, right? So if I do sorting, right? 1, 1, 2, 2, 4, 4, 4, 5, 6, right? But of course I sorted the first 10, right? But how about, right? Let's do this one more time. Let me do code, right? Sorted. Hopefully you see this, or maybe show you a little bit bigger. A little bigger, maybe? It's okay, yeah, you can see this, right? Okay, so this is first 10, right? I sorted the first 10. I sorted the first 10, right? Let's sort all and take first 10. So what do you think the first 10 will be? Right. But it looks like there's AI. Finally, they got Gemini to work. I haven't checked. They promised this for 2 years, but it looks like they have some AI assistants finally. The Google Colab, right? So you see the difference, right? Here I sort the first 10. So what do you expect the first 10 values to be? What do you expect the first 10 values to be? Yeah, all ones. Most likely they will be all ones. Why?
Why most? No.
Yeah.
Not all ones.
Okay, well, on average, we don't know yet. I don't know yet because I don't know what the particular. I didn't set a seed. I just took some random numbers. I didn't set a seed. But because you have 100 numbers, and 100 divided by 6 is like 16. So on average, right? I have 100 numbers.
Oh, you have 100.
Yes.
My bad.
Yeah. So you expect to have all ones.
Yeah.
So let's see. Yes, all ones. Yes, we got all ones. Okay, right. Right. So let's see. Of course, we can see this. Let's see the distribution. Let's see the distribution using counter. Right? Yeah, from a counter dice, and we'll show it like this. Yeah. So you can see there's actually 19 ones, right? So in terms of this counter, so here's the idea. So how could we make a sorting using this? If you know the range, it's only one. So you basically have 6 buckets, 1 through 6. So what do you do? Right? Basically, you have 6 buckets, right? 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 1, 2, 3, 4, 5, 6, right? And you have a whole bunch of numbers. You have like 1, 6, 1, 5, 2, 4, 3, 2, 2, 3, 6, right? So you just say, you go through linearly, right? Right? And you go, pick, okay, counter, right? Plus 1, plus plus, right? Plus plus, right? And so on plus plus, right? And so on, right? On plus plus, right? Counter. You have it. So if you know what you are counting, I think hopefully you can see this is very efficient, right? You're basically creating a counter, right? You only have to go through once. You only have to go through this array once. Well, what's the downside? Of course, well, are you done? You count things. Well, then you have to make this new. Then, of course, what you do is, right? You create, like 19 ones. 19 ones. 1, 1, 1, 1, 1, 1, 1. And you have whatever. Let's say you have 10, 15, 12s, right? And 2, 2, 2, 2, 2, 2, right? 15 times, right? And you have 19 times, right? And so on. So it is, so you can recreate this. It's sorted, right? By definition, basically, right? 1, 2, 2, 2, 3, 3, 4, 4, 5, 6, 6, 6. So yeah. So that's the basic idea behind these algorithms, right? And here it's a very simple example. You only have 6 items, right? Six buckets, basically, right? So you do like this approach.
Seems more simple.
Yeah, it's very simple. Like there's only one big downside is that you have to know the range, right? Now, so let's look at some of these in detail, right? So counting sort, it's efficient, stable, in place. So efficient because it beats n log log n log n, right? It beats this. It's basically closer to on, right? But not quite, right? So we could count also 10, right? 0 to 9. So we could sort digits, right? If you know we are getting only simple numbers, digits, not numbers, we take 10 buckets, right? And we can do digit list, number of buckets, debug false, right? So here I made a function to supply number of buckets, right? And how many lists, right? And debug option to see actually what I'm doing, right? So what I do is for digit in digit list, right? I go through all my list, right? So here is the basic. So this is where the magic happens. So simple. So single. So single. So single loop, right? On, right? Yeah. And we simply, again, crucially, this is O1 operation. Right? If it's not, right, then you have a problem, right? Again, you have to be sometimes careful, right? See if adding 1 to an existing, so it's a fixed size, you have a fixed sized array or somewhere some data structure, you can add +1 to it, right? Right. So initialization. So technically, okay. So this also is technically, well, init also, well, init is also on, right? So now again we haven't discussed completely formally this big O notation. So we did on twice, right? We did 2 loops, right? But they're same size, so you say, okay, this is 2n. Remember, in complexity, we discard 2 loops or 5 loops of the same thing. As far as complexity goes, they are equally good because they beat 2 nested loops, or they beat something. They will beat a single loop with some log n. If this was log n operation here, right? Then this, of course, would be automatically O n log n, right? If this was an n O n operation, right? Like string length, right? On Tuesday we talked about string length operation, right? Or we could make a bug, a nasty bug, or nasty inoptimization, or nasty, how should I say, slowdown, right? So if this was log n or whole operation would be O n log n, right? Right. Okay. Now, and then of course, this is another thing. Is we are going to make the buckets basically again. Yeah. So this should be. So this is also a bit careful. So this should be on, but depends. Right. So we create some new buckets basically, right? So this is not very, again, there could be some room for optimization. Yeah. But could be worse, language, right? Right. So, and also there's a little trick for those who use Python, how to flatten a list here, right? So, this is a little recipe from Alex Martelli. He's one of the Python authorities. A pretty good recipe how to flatten a list. So item for sublist in T for item in sublist. So it's double list comprehension. You have a 2-dimensional structure. You can flatten a list, right? Python, I don't think this is pretty good recipe. I think there might be some other options, but this is way how to have a list of lists to make just one big list, basically. Okay. So now let's see how this works, right? I'll give it my dice, right? I still have my dice, right? Yeah. So look at this here, right? It works for dice, right? 15. So let's do it. I have let's do 25, right? So as we expect, yeah, 19. We have 6 more 2s, right? How about the last ones? Let's do sorted minus 25, right? Sorry, digits. Sorry, digits. Yeah, of course, 5, 5, 5, 6, 6. Okay, so you trust me now it works, right? Yeah.
Yes.
Okay, super. Right. And also, it's interesting that right now, so this particular implementation, right? Again, it's not going to be maybe the fastest, right? It skipped the empty buckets are not shown. So these buckets, right? These are the buckets. Is nothing, right? Because my dice don't have I don't have 0 dice with 0. I don't have dice with 7, right? They were discarded in this particular operation. Okay. Now let's do some random numbers. Let's throw 20-sided dice, right? I know it's used in some, I don't know, games, right? Often on these tabletop games, right? So let's do 20-sided dice, right? Okay, so 18, min is 1, maximum is 20, right? So again, I'm double checking, sanity check, right? Also again, min and max are all operations, right? We know that already. Yeah, because again, practical consideration, maybe you made it off by 1 error again, right? Always be a little paranoid, right? Maybe you made this 1 error, right? So how are we going to sort it? So we give it this list of numbers, basically, right? 20 possible values, and we're going to sort them. We have, okay, since I'm lazy, right? Why 21? Because I don't have number 0, right? And I don't want to worry about this off by 1 errors. I'm just giving empty bucket, right? Hey, what's 1 empty bucket, you know? So let's sort it, and it should work. And again, not surprisingly, it should start with 1 and end with 20, right? Let's do like how much? So we have 100,000 random numbers from 1 to 20. So divide by 20, 50, right? So yeah, roughly 50 each, roughly, right? Let's take a look. And also I want the bug on, right? I want the bug on. Yeah, do I have the bug? The bug is true, right? I want to see that counts, right? Right. So 0, because we didn't have number 0, right? And we have all these roughly about 50, but not again. You might be asking, okay, so why when I did this random throwing, why isn't all they're all roughly 50? Of course, it's randomness, right? And there's a lot of large numbers. You've taken statistics and probability a little bit, right? Or are you going to take some?
The probability course will be in next year.
Okay, yeah. So there's something called law of large numbers, right? So eventually it's going to converge to this roughly. It's not guaranteed. It's like the gambler's fallacy. You're throwing dice. You're throwing 6 sixes in a row, right? Well, is it going to be next? Is this next one going to be 6? Right. The question is, right? Well, this is the thing. Theoretically, assuming fair dice, it should not matter, right? Well, on the other hand, if you have a friend, comes with the eagles and tails coin, right? He throws a coin, and 20 times in a row, he throws an eagle, right? Well, should you bet on having another eagle or tails, right? Well, what you should he's probably cheating you, probably, right? It's probably not a fair coin, right? He probably has some trick up sleeve. So because it's, of course, what's the probability? 2 to the 20th, so that's about 1 to the million, right? Roughly. Not impossible. Getting 20 tails or 20 heads or tails, right? Getting 20 heads, eagles' heads, right? In a row, that's about 1 to the millions, right? 2 to the 20th, right? It's possible. He's really lucky, right?
But every time you just flip a coin, it's 50-50.
Yes. So 2 to the 20th, right? 0.5, right? 0.5, 0.5, 0.5, 0.5, right? 0.5 to the 20th, right? Or 1 over 2 to the 20th, right? 1/2, right? Probability is 1/2, 0.5, right? So yeah, so it's possible, but it's most likely you should be very suspicious of him, right? Yeah, because it's not a thing. It's one thing theory, right? One thing is practice, right? Yeah. So yeah, you see some weird division. So 1 to million is not the end of, it's possible, right? If you see 1 to the trillion, right? That's 40 heads or 40 tails in a row. That's very suspicious, right? Because that's basically, it shouldn't happen in normal, right? So, but there's a story about this, about probability. It's about those. It's basically a scam. You start getting letters of stock market financial performance, and somebody says, "Okay, I'm going to tell you whether stock market goes up or down tomorrow, right?" Well, he gives you 10 correct predictions, right? And only then he said, "Okay, give me $1,000, hey, and I'll sign up for my newsletter, right?" And you sign up, right? Maybe you get another correct prediction, but then eventually you don't get a good prediction. So what happened, of course? What did he do? I say they, right? They sent 1,000 letters. You send 1,000 letters, and one of you will be the unlucky to get 10 correct predictions, right? Because 2 to the 10th, right? You only need to get 10,000, get 10 correct predictions in a row, up, down, yes, no, right? You only need on average 1,024 players, basically, right? So all the probabilities are covered, right? So one of you, right? You get 5, let's say 3 days in a row goes up, 2 days down, right? All the combinations are covered, right? All 2 to the 10 are covered by 1,024 people, right? Do you guys understand this, right?
Yes.
Yeah. Okay. Maybe we need more coffee. But okay, so going back to this, right? So for sorting, right? So it is linear time, right? But number of buckets. We could sort also. We know. Going back to my random numbers. Where did I make my random numbers? Let me check, right? Okay. Let's go my random numbers. Where are my random numbers? Oh, here, right? Let me run this, right? Or do I have it? Okay, yeah. So notice here, right? I know this has 1,000. If I know my random numbers, my 1 million numbers are in range from 0 to 999, I could use the bucket sort, right? Or counting sort, right? So when I say counting bucket, basically roughly the same buckets are just generic, right? Counting, you have specific indexing in mind, right? So so I have 1,000. So that means I can actually go down here. Where is my counting sort? Naive digit sort. Here, right? The only problem, do I need 1,000 buckets? I don't actually. I think I need only 1,000 buckets, right? No, wait. I do. I have 1,000 buckets. No, I don't need. I need only 1,000 buckets, right? Yeah, I don't need. Okay, but R1K. I think 1,000 should be enough, right? Let's try this. Or did I make mistake? The bug is true. The bug is true. I think this will work. Let's try it. Oh no, I don't know. I can't debug. I don't need to debug. Let's see if it actually works, right? 1,000. I think. Oh no, it doesn't work. List index out of range. All right. Wait. Let's think about this. Or did I make it R1K? Oh, let's see. Oh, max. Oh, yeah. So, yeah. All right. Okay. That's why I did minimum maximum. That's why you have to check. So, yeah. So, here's an approach you could take to do this counting sort in general case. We have a linear. We want to keep this linearity. So, minimum we can find in linear time, right? R1K. 495 is the smallest. Right. So, we actually have a 1,000 items, right? And length, right. We have 1,000, right. So we have random numbers, right? Yeah. So 1,000 numbers. Minimum is 495 and maximum is 99884. So range is technically from 0, but okay, 495 is the smallest. The biggest is not quite the million, 999, right? Okay. So that's why we need 1,000 buckets is not enough. We need 1,000,000 buckets. Well, okay, 990,000 something buckets up to 884. You can use this number, right? You can use this number here. In this case, don't oh, Control Z, can't Control C, but not much different. Right. Okay, now let's do this one more time. It will work. Right, it's sorted. Amazing. I sorted using this digit sort. But if I time it, it's going to be pretty horrible. Let's not do the bug. Maybe let's do the bug here. One more time. Right. Okay, so it works. And you probably trust me, this works. But if I try to time it right, it's not gonna oh, time it. What's the problem? Oh no, I need 1 million buckets there, sorry. Yeah, the issue is 300. Remember, I only have 1,000 items, right? And I spent 300 milliseconds. And sorting is microseconds, so it's about 1,000 times slower, right? So, what's the takeaway from this is? What's the problem? Because I already mentioned this in the comment, right? We are spending too much time creating these buckets, right? So, it's one of those ideas in algorithms. You can spend some time doing some work ahead, right? You're not going to be doing some heavy work later. You prepare. You set some time. You set some memory, doing some pre-calculations, setting the right data structures. So it's sort of paid forward, right? So then, when you actually need to do lots of work, quickly, right? You are ready, right? It's like preparation, right? It's just like that. If you have like a midterm or exam, right? You don't. If teacher lets you prepare, right? Maybe do some, do some stubs, some code fragments, maybe do something, right? You don't start with nothing, right? Or if you're taking the school exam, right? You can have some formulas, things like that. You can prepare. You don't have to go look it up, right? Okay. Maybe not a great style analogy. Okay, so that's why this buckets or counting sort is not quite great, right? Here's the same idea. Now, so counting, you don't have to counting sort. You can sort code other things. For example, you could use it to sort letters in ASCII code, right? 256 different values to work, right? And again, you don't need to compare them. Again, as long as for extra, if you did Unicode with emojis, for emojis, it's set there, right? Emojis. Now, let's do this. Oh yeah, you can sort, RTU, RBS rocks, sorting not that bad, and you have it sorted. Again, so now you see the issue with this, right? If you have a lot of, million possible values, need million buckets, can you do something about, is there some sort of middle ground? What's one idea? You have this big number, for numbers, for example, something called Radix sort. Let's get to this Radix sort idea. Radix, I don't know how you say in Latvian, Radix. Radix. Karta, how do you translate this? Basically, you have if you can sort 10 items, right, by 10 buckets, right? Well, you don't want million buckets, but what if you could sort each position in a digit using this sort? So idea you have like 5, 6, 3, 8, right? You use this one 10-digit sort, another 10-digit sort, right? And this is basically the idea behind Radix sort. You sort each position individually, right? So this is actually sort of a good middle ground. You don't need 10,000 buckets to sort 4-digit numbers. You only need, you need basically one 10-digit bucket basically to use it as a sort of like a storage. So very cool sorting algorithm. And again, it beats. So what do you think its complexity is going to be? Any ideas? Well, you have depends how many items you have, so n, right? But what's the other, where other complexity will be? Well, 10 digits, that's fixed, right? 10 digits, that's fixed, right? So what does it depend on? Let's see. Well, so you have this n, so you have n items, you have n, you have n elements, right? Right, as usual. So O, n, but something else, Radix sort. What other factor is flexible? If you have digits, if you have numbers, it's going to depend on what factor?
How many numbers?
How many digits you have in a number? How many digits? Like if you have something like 9 million, 9, 5, 6, 7, 8, 1, 8, 1, 2, 0, 1, right? So k digits, right? Right. That's going to be flexible. If you have only single digit numbers, right? If you know for sure, but if you don't know, right? This is a variable, so it's actually n plus k, right? So it's not n log n. It's actually two different variables, basically factors, right? N meaning being a number of elements, and k number of digits in this element, right? So that's Radix sort, right? Let me see if there's also counting sort, so bucket sort, right? So you could also do some sort of normalization, right? So Radix sort, right? You group the keys by individual digits. It's really cool. You don't compare it, right? So actually n times k, I'm sorry, n times k, right? Let's double check again if I am completely off my mark. What did I say? N plus, I thought n plus k. No, Radix sort n times k. Okay, yeah. Counting would be n plus k, but n times k actually. Right. So let's see this in action. I think I have it somewhere in action. Yeah. All right. Here's my okay. Implement Radix sort, right? Yeah. Don't go to the code. I just want to show you. I know you guys are pretty tired. I want to show you the visualization of this Radix sort, right? Stable and stable, right? Where is my Radix sort visualization? Radix sort visualization. This one here, University of San Francisco. All right, this one will do. Okay, so you have what, 3 digits, right? Maybe 4 somewhere, no, 3. Okay. You have just some random elements, right? And this is going to be, we need this middle bucket sort of. So we need extra storage for Radix sort, right? We'll be moving things around like a temporary storage, right? So we're going to sort by the last digit first, probably, I think here. Let's take a look at this. Pause. Okay. So first part is easy, but look at this, what we are doing. It's kind of weird. We're going to look at the last digit. We sort by last digit, right? We're going to put some counts for last digits. Right? Easy, right? Linear. So you have to do it. So that's why n times k, right? You have n elements, k times, right? K being, 3 times. In this case, k is 3. Because you have up to 3 digits, right? Do we have like, what will happen is 4, right? Are we going to have any zeros? Yeah. Yeah, we have some zeros too. Right? Can you see this maybe a little better? Like this, okay. All right. Easy, and I'll just step forward quickly. And so now, okay, so this is the easy part, right? And what do we do with this information? Before we go to the break. Okay, so we have 4 zeros, right? So we will adjust this. Let's take a look. So what's happening here? Basically, these are going to be offsets where we know the offsets. This is going to be 11, I think, right? Yeah, 11, 15. Wait, yeah. So there's no 5s down. Yeah, there's no 5s. Okay. 17, and this is going to be 23, right? And this is going to be 24, and that's going to be 30, right? Well, obviously, right? So, what do these numbers mean now? All of these counts, we generated the offsets, the pointers to the right position where the number should be. So we'll take 9. We know, of course, it will go where? It will go in this position. It will go here. Okay, off by 1 errors on the top of my head. I'm not sure. Either here or here. Either 24, 25. Let's take a look now. Or I'll start at the beginning. Okay, we start at the end. Sorry, we start at the end. So now it has 9. Okay, where do we put it? Here. Okay, we put the end. Okay, offset here. And we decrease the counter, by the way, right? Now, that's the number 22, right? We know the offset. That's 9. It goes here, right? Yep. Or actually 8. Sorry, it's off by an error, right? And we decrease the counter. Now it's 9, right? Zero-based indexing, right? Again, very easy to make mistakes. So 6, where it will go? It will go at 17 or 16. I'm not sure. So I think 16. I think, yeah. Yeah, it decreased to 1, and then it puts here. Yeah, okay. Right.
How were the offsets calculated?
From the counting, you generate the counts of the last digit.
Yeah.
From the last digit, generate counts. It means when you're going through the numbers, you know where to put these numbers because you know the last digit, of course, right? You see, okay, last digit 7. We have this lookup table, right? And we know, okay, it should go this position. If it's 7, it should go here, right? So this is a very efficient way of putting. So basically, we need this sort of holding area, right? So what this means is, by this moment, when I do all this, right, these offsets, right? Okay, so 7, 22, right? So this means this keeps accurate positions of where the next number should go based on the last digit. That's all it is. And at this moment, I think it's not clear how is that actually gonna. Isn't this gonna like aren't we doing reverse? You're counting by last. You're sorting by last digit. Isn't gonna all mess up with the first digits? What's gonna happen then, right? So let me go quickly through. Hopefully you can trust me on this moment that it's actually sort. It's gonna be sorted by last digit, of course, right? Let's do it quickly. Can I skip forward? No, it's all sorted. Sorry again. I'll do this faster.
Press play.
Yeah. So let's do this. And so the last digit, since I'm lazy, hands off. Right, now it's going to build the offset table, right? And now goes through one by one, where to put it. And then I'll pause it. And I think that it will move it. Now all of this data will be moved up here, basically, right? So that's a memory copy. Right, so let's take pop. Okay, so you can see here, right? Right, so at this moment, it's sorted by the last digit. Makes sense? We copy, see, we moved away, right? So we move it here, and now, of course, we're gonna count the second digit, right? See, 6, right? I'll play. All right, and again, we'll generate offset tables. Again, very easy, right? So we know I guess there's no 8s. I guess there's no 8s whatsoever, right? So there's only 7s and 9s. It looks like, right? Yeah. No middle. I see 8 here. And there's 9 here. Okay, we'll see. Why isn't there only one 8 here? We'll see. Oh, okay, we'll see. Let's play. So hopefully now, look at what's happening here right now. Do you see what's happening? It's already sorted by last 2 digits. You see? 72, 76, 77, 77, 79, right? So hopefully now you trust me, right? So now it's sorted by last 2 digits. If you ignored anything in the beginning, right? it will be sorted. 4, 14, 18, 22, 23, 23, 32, 34, 37. And now, of course, we'll do the same for the third one, and so you can do it for fourth and fifth and so on, right? So it's a really beautiful algorithm, really nice, and it also has potential to sort, to beat n log n. So my question might be why it's not used more than, say, tim sort or Radix sort. Well, there's quite a bit of overhead, right? It's a big setup time, this movement, right? Theoretically, it's a special case, it might be faster, but if you do your naive implementation, you're not going to beat tim sort actually, right? So right now, it's going to be all nicely sorted. Yeah, now we just got copy. Yeah, and it's sorted, right? So we did 3 times. So k was 3, n was 30 here, right? So we don't use too much in practice because it's just a setup time. This actually algorithm was used in tabulating for like statistics when you did before computers. Like one of the start of IBM was in the late 19th century before computers, right? To tabulate census, you know, when you go around asking people, right, ages, gender, all that good stuff, right? So they had these cards, right? And how do you count them, right? You use something like this basically then. Okay, so today what did we learn? We learned about quicksort, how you sort to me.
No, nothing.
Yeah, so how important it is to pick a good pivot for quicksort. We learned about heap sort, where we learned that you can use an existing structure if it has a specific time, and use a bad algorithm, make a good algorithm out of it by using a better data structure. And then we learned about tim sort, which is basically hybrid strategy. And then we learned how to beat n log n by using special counting, basically counting-based approach. Okay, so that is basically a basic overview of sorting algorithms. Let me show you more sorting algorithm visualizations. There's one more which I didn't mention here before. Visual algo, we saw top-down. There was, I think, this one, yeah. This includes all of the bad ones, yeah. Sort visualizer, you can play around with this one also. Because also, if you know a little bit of JavaScript, you can also add your own. Pretty simple, right? Sorts. Logarithmics, quicksort, merge sort, keep sort, quadratic, the bad ones, and the weird ones. There's a BOGO sort, right, Radix sort, but weird is Radix sort. Well, it's actually, let's say it's bad, it's good actually, right? But it's not going to show, you see here from this visualization, you can see how Radix sort works. The one I showed you was better, I think. But it's kind of cool for just watching, right? Quicksort, for example, right? So fix pivot, and then it will be finished, right? Come on, do it, do your work. Right. So it's kind of cool, but I don't think you learn much from this one. But it's good to maybe play around with it a little bit. Right. Okay. So what are we gonna cover next? Let's take a look. 24. Next week we're gonna look at master theorem. Finally, this is the only theoretical lecture. The only one where we maybe don't do too much programming, but we actually learn how to produce complexity, the actual number, big O notation, given some sort of recurrence. We come up with an algorithm, and we can come up with a complexity. Okay. So thank you. We'll see you guys in about half an hour. No, let's see in about 25 minutes. All right. So 10, 11. Let's start. Actually, let's be 11:15. 11:15, so give you a little time.